Consider the following problem. Scott is hiking the Appalachian Trail from Georgia to Maine. The distance of his hike is 2,200 miles. It took Scott 123 days to complete the hike. The data below represent the distance d he had hiked t days after the start of his trip. If we look at the following table, notice that here we have a series of different input values, how many days he was hiking, and then we have an output value, which is how far he had traveled at the end of that day. In this particular case, if you look at it carefully, you'll notice that he didn't always hike exactly the same amount every day. And so when we go to make a linear model, this is not perfectly linear. So what we want to do instead is find what we call the line of best fit. In order to do this, we have a mathematical representation that we can, and mathematical set of calculations that we can make, and that process is called linear regression. Linear regression is fairly tedious and is most easily completed by using technology. In this video, we'll be solving this problem, finding the line of best fit, by using Excel. If you have a TI graphing calculator, you can also do linear regressions on the graphing calculators, and you should watch the video previous to this one in the playlist for instructions on how to do the same problem using a different technology. All right, so if you are going to do this using Excel, the first thing that you need to do is go ahead and load up Excel, and I've got just a blank book here. What I'd like to do to begin with is to go ahead and enter in each of these different values for the number of days that he was hiking in list 1. So we want all of our inputs to be in list 1, and we want all of our outputs, in this case that would be the distance in miles, to show up here in list 2. So let's go ahead and do that. So here we're going to have 0, then 32, 47, 73, 99, and 123. Then we're going to go over into column B, and we're going to type in all the output values, and it's important that you do put them in that order. So 0, then 590, 912, 1,212, 1,876, and wrapping up with the 2,200 miles for his hike. All right. Once you have all the data entered in Excel, what you want to do is highlight all of those numbers, both just only the values that you actually have typed in each of those applications. The next thing that you want to do is to click on Insert, and what we want to do is look at a scatter plot of these points, because it's good to see if we can if these points actually look as linear as we think they probably are. Under the Insert menu, you'll see a little thing under here under Charts. There's an option that looks like Scatter Plot, so click on that and just go ahead and choose this first option for the Scatter Plot graph. Now if you look down below here, you'll see if we plotted these points, we can't draw a straight line straight through it very well. However, it does do a pretty good job of being mostly linear, and so we should be able to come up with an equation that's going to work fairly well for us. So how do we find that equation? Well, we're going to go ahead and click on this plus value up here, and it's going to bring up some options for us. What we're interested in here is what's called the trend line. So go ahead and click on the trend line box at the bottom, and then we want to click on the arrow and we want to choose more options. As we come over here, I'm looking for the line of best fit, so I'm looking for a linear trend line. So make sure that that bubble is the one that's selected. And then if you scroll down to the bottom, you'll have a couple of options that we want to make sure that we use. One of the options is to display the equation on the chart, and the other option is to display the r² value on the chart, and we'll talk about what that means here in just a minute. Now, if we go back to our plot area, let's go ahead and close this side window here so we can see our chart, since I'm on kind of a small screen. Notice up at the very top there, it's kind of small print, but you'll see our equation, which is our line of best fit. Y equals 18.007x plus 9.2217. And then we have that r² value here we'll talk about in just a sec. And kind of a nice little plot there that we can look at, and you can see that this line here kind of goes through the middle of those points in the very closest, most accurate way possible. All right, so how do we transfer all this information in order to answer our questions? We now have enough information to be able to do that. First of all, notice that that Excel gave us the equation in the form that we need for here, where it asks us to write it in the form of y equals ax plus b. So our equation of the regression line, sometimes you'll see it called the line of best fit, is just going to be y equals 18. The problem asked us to round to 2 decimal places, so we'll just say 18.01x plus 9.22. That's going to be our y equals ax plus b form. Now, here we also would like to write it in function form using the variables that they laid out for us as well. Normally, our input variables are x and our output variables are y. Here, the problem would like us to use t for the input and d of t for the output. So we can just replace those here. So our output is now d of t equals 18.01. Our input we want to use as t for the time in days plus 9.22. So these are our nice formal equations that are our line of regression and our lines of best fit. The next problem here asks us to look at the scatter plot of the data. Well, Excel did that nicely for us already. And just based on the picture, we can see that it's not exactly linear, right? That line does not go through every single point. However, it's pretty darn close. So I would call this approximately linear. A more mathematical way to look at this is to look at the r value, or in this case, the r squared value that we are given. Here, our r squared value is 0.993. Now, if we have r values, what does r even mean? R is what we call the coefficient of correlation. And what it's doing is it's saying how good does the data set match up with the equation that I've written? How far off is it? Because the truth is you can put any data into Excel that you want, and it may or may not look like a line. It'll come up with the very best possible equation, but it may not be a very good one. So the R value gives you an idea of how well should I trust this data. When we're looking at R squared values are always going to be less than or equal to 1. And so we're looking at R values in between here and here. My general rule of thumb is the closer, if it's exactly equal to 1, that means it's perfectly linear. So in this case, we are really, really close to 1, right? By having an r squared of 0.993, we're really close to 1. So since my r value is close to 1, I can trust my data fairly well. And my equation is definitely, or the data points are approximately linear as we go through here. The farther away you are from 1, the worse it is. I kind of tend to use kind of like a grades analogy. If I'm in the 90%, like 0.9 to 1, then this is pretty darn good. My equation does a relatively good job of approximating the data. If I'm in the 80s, it's okay. And once we get in the 70s, it's not quite as good. And as we get lower and lower, then we're failing, and we really don't have any grasp of what our regression value sets are. So in terms of a question like this, I would look at the scatter plot, look at the R value, and then I could say that my data was approximately linear because the points were close to a line and my R value was close to 1. The next question asks us to find the slope of our regression model and then describe what it means in the context of our problem. Recall, if you think of our general equation, we think of y equals mx plus b, and our slope is always the coefficient of the x term. If we look up here then, that means that 18.01 is my slope. Well, what does that mean? If you have trouble identifying what that would mean in the context of the problem, first of all, remember that slope is related to a rate of change. So it's talking about how things are changing. If you want to go back and identify units, something that I find is really helpful to do is to remember that to think of the slope formula. If I think of the slope formula, my y-coordinate or output values are on top, and my x-coordinate or input values are on the bottom. So if I come up here, notice that my output values were miles, distances in miles, and my input values were the number of days that were spent hiking. So if I want to think in terms of what my units are for this 18.01, what this means is miles per day. And what the interpretation is that as Scott is going on his hike, he is hiking about 18 miles a day. And we know it's not 100% perfect because it's only approximately linear, but pretty close to that in terms of his hiking across the trail. Now, once you have an equation, so it's kind of cool to see that these numbers actually have some validity and meaning. Once you have an equation, though, we call that equation our model. So this is the equation that we found using technology. And so in this case, that was our Excel. So using the equation that we found, we want to estimate the number of miles that Scott had hiked in 50 days. So to do that, we want to find D when our input is 50, so we just put 50 in for T. Should be able to just evaluate that on your calculator. It comes up pretty well. Let's get back to the main screen here. If we do 18.01, oops, 01 times 50 plus 9.22, we get 909.72. So we would expect that in 50 days, he would travel 909 miles. Let's see how well that, so that's according to our model. Let's see how well that matches with what we're going on up here. 909 miles in 50 days. It's a little bit less than how much he traveled in 47. So he was hiking a little bit fast up front and kind of slowed down a little bit towards the end, which I guess only makes sense. He probably got kind of tired. All right, the last question that we have here is using our model, estimate when Scott would have hiked 1,000 miles. We're still going to go back and use our equation, but this time we know the distance. So we want to put that over in the output location of my formula. So we're going to let D be 1,000, and then we want to find T this time. Now this is just a simple linear equation that we can solve. In this case, we'll minus 9.22 from each side first. If we do that over here, we get 1,000 minus 9.22 is 990.78 equals 18.01 T. Divide both sides by 18.01. And this will give us, so we'll divide our last answer by 18.01. And that gives me 55.01 days. And that kind of jives with what we were looking at here. He hiked 909 miles in 50 days, so it would be about 55 days before he'd get to the 1,000-mile mark. Just a few more days on his journey. So as we're going through again, we can use technology like Excel in order to sketch a graph, find the best fit equation possible, see how good of a fit it is, and if we like how, if we like how good of a fit of an equation we have, that does not want to close, there we go. If we like how good of an equation we have, then we can use it to make predictions, which is pretty awesome. In the next video, we'll look at how to do different kinds of regressions. So if our graphs don't look like lines, maybe the points look in a different shape, then we can find a different kind of equation as a model.